So today is section 7.2, separable first order differential equations, uninhibited and inhibited growth in decay models. Students will solve a separable first order differential equation and solve differential equations involving uninhibited and inhibited growth and decay. We'll get more into the inhibited and uninhibited growth and decay in another section. So this is incorrect. Forgot to update my notes, so we don't need that. So let's jump right in. Separable first order differential equations. A first order equation is said to be separable if it can be written in the form dy over dx equals m of x over n of y. Yes, it's helpful, but what we really need is this version. All the y terms are on the left. All the x terms are on the right. That's really what everything in this yellow box is saying. Our steps to solve a differential equation are to isolate dy over dx, put all the x terms together and all y terms together. This is really the big deal. We're going to find the antiderivative of both sides, solve for y, and then substitute the initial conditions to solve for c. So we did this a little bit yesterday, but they were the ones that didn't separate, or they separated very easily, or we didn't have to separate. When we moved the dx to the right, that was basically separating them. So I have dy over dx, already isolated. I have 3x over y squared. So what I'm going to do is multiply both sides by dx. So great job. On the left, I only have x terms, but on the right, I have x's and y's. So now I'm going to divide by y squared. So because the left-hand side is all y and the right-hand side is all x, we're ready to integrate. So on the left-hand side, not natural log, it's y to the negative 2 dy. On the right-hand side, I don't have to do anything special there. I'm just going to rewrite it. So the antiderivative of y to the negative 2 is y to the negative 1 divided by negative 1. Yes, I know there's a plus c there. On the right-hand side, that would be 3x squared over 2. There's a plus c, but it's a different plus c, so I'll call it c sub 2. Our job is to solve for y. So I'm going to subtract the c1. I'm also going to rewrite this as negative 1 over y to the first. 3 over 2 x squared. c2 minus c1. Now, a couple things here for us. The first, a constant minus another constant is just a constant. So this is just plus c. And because of that, we don't usually bother writing this one over here. We keep the plus c on the x side because we know we eventually want to solve for y. So we don't actually have to write the plus c and subtract it over. I just want you to show, just for you to see where it goes. I am going to do a little bit of rearranging. I'm going to multiply both sides by y and then divide by this quantity. So I wind up with a negative 1. 3 halves x squared plus c is equal to y. So if you need to write out the separate steps, multiply both sides by y, and then divide by that 3 over 2 x squared plus c. Now, this is our general solution. If we want the particular solution, we need to solve for c. So I'm going to come over here on the left and do that. So I am going to have negative 1, 3 over 2. I know the x value I have is 1 plus c, and the y value I have is 2. So if I rearrange this a little bit, I've got negative 1, 3 over 2 plus c is equal to 2. I'm going to multiply by the denominator on the left and divide by 2. So negative 1 over 2 is equal to 3 over 2 plus c. If I subtract 3 over 2 on both sides, I have a negative 4 over 2 is equal to c, which is negative 2 equals c. Sorry, I'm out of space here. So again, negative 2 is not my answer, but rewriting the equation with that c in there, that is my final answer. So this one's your particular solution. All right. Good job. I was about to say, have any questions, but if you have any questions, reach out to me. All right, differential equations with growth and decay. So I would ask if we were in the same room together, I'd say, do you remember growth and decay from pre-calculus? And hopefully you would say yes. And then hopefully you would tell me something about the PERT formula. And I say that because you spend a lot of time on exponential growth, and I think you use this one with money, compounding continuously. You have your initial principal and your final principal. You could use it for population. Sometimes the letter A is in there, and instead of R, we use a T. We're going to talk today about a Y and a C and an E to the KT. These are all the same form. They're all exponential growth. We're just switching the variables for depending on what we're talking about. So if you remember the PERT formula, great, keep remembering that. I'm probably going to use these kinds of variables, but sometimes I'll go back to PERT just because that's what we know. So if the quantity A varies with time in such a way that the rate of change with respect to T is proportional to A itself, these situations can be modeled with the differential equation. So we can write it as dA over dt. We can write it as y prime. Growth model if K is positive, then your rate of change is positive. And if K is negative and your rate of change is negative, that's decay. So we're going to derive the solution to the differential equations. This means I'm going to show you once, and then you're just going to use the solution. So we have, let me make this a little bigger. We have dA over dt is equal to Ka. This is a separable differential equation, a skill that we just had in the first example. We're going to use here. So I'm going to multiply both sides by dt. Then I'm going to divide A to the left-hand side. I want A's on the left and T's on the right. Cool, we've separated them. Now we're going to integrate. The integral of dA over A is the natural log of A. K dt, I know I have all letters, but K is a constant. I know we use the word variable, but it's a variable in that it's unknown as opposed to changing. So it's a constant value that's unknown right now, but we'll be able to figure that out. So the antiderivative of K dt is K. T is my variable, so I add that on plus C. So now my job is to solve for A. So how do we do that? Introduce E on both sides. Natural log of A equals K. Whoops, forgot the E. E K T plus C. Great. On the left, we know the E and the ln are inverses, so I'm left with the absolute value of A is E to the KT plus C. Two old math rules here that we need to address. I'm going to come over here to the left. If I had x squared and x to the third, you would tell me that's x to the fifth. We add those exponents. So if I write this in between step, 2 plus 3, all of these are equivalent, right? So if I have 2 plus 3 adding the exponents, I can turn it into multiplying the bases. So that's exactly what I'm going to do over here on the right-hand side. This is E to the KT times E to the C. I know this looks a little bit weird. So with my log rules, E is really 2.7. 2.7 raised to a constant is still a constant. So this is the absolute value of A is E to the KT times C. And we'll bring that to the front. Okay. One more thing that we have to deal with here, and that's the absolute value that students like to ask me about. If you remember, I'm going to do this on the side. The absolute value of x equals 6, we would write that as x equals 6 and x equals negative 6. So if I take that idea here, okay, A is equal to CE to the KT. A is equal to negative CE to the KT. But here's the thing, a C and a negative C are still both a constant. So I don't have to write them separately. So that absolute value really gets absorbed into the final answer. So our final answer is EC to the KT. Now, you don't have to do this each time. What I need you to remember is that if you have this situation, then you can use this formula. So it's a new way of asking you or giving you the directions on these exponential growth equations. So you don't have to separate the variables and do all this process again. We're just deriving the solution to prove that it works. The counter to that, or the opposite side, just to show you, I'll do it over here. If A is equal to CE to the KT, I find the derivative dA dt. The derivative would be CE to the KT times K. Well, I know that CE to the KT is the same thing as A. So dA dt is going to be A times K. Just like we had up here. So I just want to show you that these two things are related. If you have this situation, then this is true, same in reverse. If you have this situation, then this is true. So that's what we really need to know. Example 2, suppose that a colony of bacteria grows at a rate proportional to the number of bacteria present. If the population doubles in 5 hours, how long does it take for it to triple? So here's what I need you to know for the calculus piece. The colony grows at a rate proportional to the number of bacteria present. So because the bacteria grows, so that's the growth of the population with respect to time, at a rate proportional, K is my proportionality constant, to the number of bacteria present. So A is the amount of bacteria present. If this is true, then I know that I can go right to, all right, this is A, C, E to the KT. So if the population doubles in 5 hours, that's what we're going to use first. So again, if we know that that rate is proportional to the number of bacteria present, then we can use, our version of the PERT formula. So I just have different letters, but it does work exactly the same way. So if the population doubles in 5 hours, that means I have twice as much at the end as I did initially. You could use 10 and 20, you could use 50 and 100. You can use 2A and 1A. Some students were doing that. I know I have E, here's K, and my time is 5 hours. So how do we solve for K? We need a natural log. Natural log of 2, natural log of E to the K 5. I know the natural log and the E are inverses. So I've got natural log of 2 equals 5K. Divide both sides by 5. So natural log of 2 over 5 is equal to K. Yes, you could put that in your in your calculator to get a decimal. Keep at least 4 decimal places because your answer needs to be correct to 3 decimal places. I'd even keep 5 decimal places. But we want to know how long does it take for the population to triple. So we have to do this problem again one more time. So how long does it take for the population to triple? So if I have 3 times as much as I started with, E, this time we know what K is. It's the natural log of 2 over 5. And T is what we're looking to solve for. So just like the first time through, we'll use natural log of E, ln of 2 over 5 times T. I know that's clumsy to write, but that's okay. Natural log of 3, natural log of E on the right, that becomes 1. ln of 2 over 5, this is times T. You would divide both sides by that quantity in parentheses. This is equal to T. So when I divide by a fraction, it's the same thing as multiplying by the reciprocal. So I've got 5 ln of 3 over ln of 2. So that 5 flips up to the top. This is your time. And again, you could turn that into a decimal to figure out what that actual time is. All right. A radioactive substance has a rate of decay is proportional to the amount of substance present at that time t. The half-life of a radioactive substance is the time required for half the substance to decay. Because it's never gone completely, we can measure half the time, but you'll never be able to measure the amount to 0 because it will never reach 0. So example 3, this is carbon-14 dating. The skull of an animal found in an archaeological dig contains 20% of the original amount of carbon-14. If the half-life of carbon So this is my clue that it's exponential. If the half-life of carbon is 5,730 years, how long ago did the animal die? So I'm going to jump right in. A equals CE to the KT. Again, you can use the PERT formula if you're more comfortable with that. So half-life is how long did it take to wind up with half of what I started with. So if I start with 1 and I go to 0.5, 1, whatever we're talking about, E, my rate is what we're looking for, and half-life is 5730. So we're going to solve for K. Natural log of 0.5. I know that the ln and E will cancel out, so I've got 5730 times K. If I divide both sides by 5730, natural log of 0.5 over 5730 is equal to K. Now, we're going to do a little natural log math. 0.5 I know is 1/2, so this is natural log of 1/2 over 5730, which is the natural log of 1 minus the natural log of 2, if you remember those rules. And what's the natural log of 1 the same thing as? That's a 0. So negative natural log of 2 over 5730 is my K. That's our rate. So we'll do the whole thing again. And the question is, how long or how old is this? If there's 20% of the original, how long ago did the animal die? So I know I'm solving for T. So my final amount is 20% of the original. So this is really 100%. Here's my 20%. I had a student also say 1/5, also correct. E to the KT, well, now I know what K is, negative natural log of 2 over 5730 times T. We know we need a natural log on both sides. And this would be negative ln of 2 over 5730 times T. And to solve for T, we'll divide. So natural log of 0.2 over negative ln of 2 over 5730. I know this is really clumsy. Let's see, you could tell me. Well, we can do this a little bit further. Let's take our 0.2 and make it 1/5. I know at this point you probably pulled out your calculator, but if you're still listening. If I use the same idea before as division becomes subtraction, natural log of 1 minus natural log of 5 over negative ln of 2 over 5730. Natural log of 1 is 0. My two negatives would cancel out. The 5730 would come to the numerator. So this would be 5730 natural log of 5 over the natural log of 2. Fun with logs. So you could get me a decimal number. I think it's around 13,000 if I remember correctly, but that is your time. So exponential growth and decay is kind of fun. It's used in money, it's used in science, biology, physics. I know that you've done example problems with those before, but this assignment should feel very familiar. It should feel like pre-calculus, and that's okay. Let me know if you have any questions.